I have some giveaways. First things first, wonderful Shmoo Moose. All right, now I have less moose than ever. That joke didn't go over so well. I know it's a little cold today outside. I have a blackberry hat. One in the blue. From No Starch Press, the Essential Blender. It's a 3D visualization and development open source suite. I don't want to throw books. I heard somebody last year. And of course, the most awesome prize, a Shmoocon branded mag light. I'm not going to throw that either. While mag lights are resilient, I don't want to smack somebody up upside the head with some metal. Okay, so there's a slight change in the speakers today. Ashley Thomas could not be available, so we have a replacement. Come on up. And I already forgot. All right. So without further ado, tracking flaws in streamer assembly and snort.
Thanks for coming out to the talk. Thank you. My name is Ben Feinstein. I work for SecureWorks. I lead a team that does our network countermeasure development and also is the tip of the spear for security operations. My colleague Ashley Thomas spent a lot of time and effort on this project, and it's very unfortunate he had a family medical emergency about 12 hours ago and was not able to attend. I hope I can do justice to all the work you put into this, and I'm going to do my best to deliver a great talk, so please don't hit me with too many shmoo balls as you go through this. So Ashley Thomas, he's a software developer on our IDS/IPS team. He's spoken at a number of conferences, RAID, information assurance and security conferences, holds a SANS GCIA Gold. You may have seen me speak at some other conferences as well, though I'm very pleased that this is the first opportunity I've had to deliver a talk at Shmoo. So just sort of a brief agenda. I hope it's not too remedial for the crowd, but we're going to cover a little bit of background around IDS, IPS, sort of the different approaches of IDS and IPS, and also some of the trickiness of TCP stream reassembly. Talk about that problem, and go over some experimental results and some findings around some tricky corner cases to stream reassembly and some of the design trade-offs that are involved there. And time pending, I'll try to take some questions and answers at the end. So on to background. Really, I think the initial concepts of intrusion detection, not to say network intrusion detection, but the general concept really came out in the first paper in 1980. And then in the 1990s or the early 90s, it became a network intrusion detection kind of system concept. Early on, it was all about basically looking at audit logs from mainframes. That was essentially the concept in 1980. L. Todd Heberlein from UC Davis in 1990 published a paper about the Network Security Monitor, or NSM, which was sort of the seminal paper introducing network intrusion detection concepts there. So a lot of the history of network IDS really involved DARPA, United States Air Force, and government organizations. The U.S. Air Force developed their own intrusion detection system called ASIM, or Automated Security Incident Management System, and that was used, it possibly still is used now, I'm not certain. You know, the illustrious Marcus Raynham came out with Network Flight Recorder, which was eventually acquired by Checkpoint in, I think, early 2007. And there's some other historical IDSs if you want to kind of do some research there. Cisco NetRanger was an early one. So as I was kind of trying to piece together the history here, of course I ran into posts from gdead@shmoo.com to some lists, or going by B. Potter, back in 1999 talking about these things. So, you know, kind of rediscover some of the history here, going through old Usenet and newsgroup postings from 12 years ago. So IDS was initially about passively monitoring either, initially just audit logs from mainframes, but then network traffic. And people started to think, well, is there a way I could prevent this? The sort of detect, react, respond cycle was troublesome for these organizations, where they detect an attack, but then they had to respond to that with some other system. So early attempts were done basically TCP resets. You're sitting there out of band on a network, and the hope is you can win a race condition against one of the two peers. Very simple stuff. Early integration with firewalls. There was a Snort SAM, which was a plug-in for Snort from Frank Knob, who would basically talk to a checkpoint firewall and dynamically manage access control lists. And then eventually we got to the point where we're truly running an inline IPS. Essentially, the early ones were essentially bridge devices, bridging traffic across different networks and applying policy based on the inspection going on there. So the newer developments, Snort has now abstracted away the guts of whatever packet acquisition or inline technology you want to use with something called DAC. I think it's data acquisition layer. So it's a nice abstract API framework. And they've recently posted some good blogs on how you can actually write your own DAC modules, and some of the auto tools, troubles are sort of laid out for you there. So it's important to think about the ancestry or heredity of a lot of the current IPS systems out there. Most of them began their existence as an IDS and then eventually added on IPS capabilities and inline capabilities. So sometimes you find that architecturally or in the core of some of these technologies, there's still almost an IDS under the cover, in that some of the architectural or some of the design decisions that went into the product in its early years or the project were really oriented more towards an intrusion detection approach versus a prevention approach. We'll get into that a little bit later. So what has been the innovation in the world of network IDS IPS? What's the trend, the direction it's been taking? Well, really, it's dictated by how the threat landscape is changing. It shouldn't be news for anybody here, but the past decade or so, the threat has really moved up the stack, away from people attacking network services like SMTP and POP and IMAP, to actually attacking the applications that ride on top of all these protocols. The biggest of which is, of course, the web and HTTP, but there's a lot of other application layer attacks out there. And also, one of the other trends is the move from server side to client side. So obviously, all the defensive technologies, the defensive solutions really followed suit. As the attackers moved their focus away from the servers, the defenders had to also adjust their tactics to control that. So what we've seen really is then a focus in all these solutions onto the application layer, protection and detection, and somewhat the focus has moved away from the lower levels. Here we are, it's 2011, you're listening to a talk essentially about corner cases of TCP reassembly. Well, some of these techniques or some of these technologies still have some flaws. It's a very difficult problem, and there's many complex design trade-offs at play. The perfect TCP stream reassembly IPS module, the perfect one, could never work. The performance, the latency issues it would induce just would make it operationally infeasible. So, you can't expect the perfect reassembly algorithm. It's all about looking at what are the design trade-offs the designers are making and the architects are making, and looking at certain corner cases and seeing what is the implication of this reassembly strategy, this flushing strategy. So I found a quote here online, and a respected person had said that network IPS is nothing but a network IDS with additional capability to protect and react. The signatures and functionality are essentially the same. So if you think about that statement for a little bit, who all would agree with that statement, that they're really basically the same things? Well, I would say I disagree in that there's a lot of design decisions and architectural trade-offs that you want to make different decisions for based on, are you focused on a prevention, inline prevention kind of mode, or are you really focused on a passive or out-of-band detection mode? There's all sorts of considerations. If you're inline, essentially your device is responsible for passing these packets or these frames across these network devices. You've got to worry about inter-packet arrival delay, jitter, drop packets. If you cause packets to arrive in a different order out the other side of your inline device as they arrive, that can be an issue. And you also have to be concerned with the wide variety of networks out there. It's constantly amazing to me based on monitoring thousands of networks out there, the variety of traffic, the dirty network traffic we see, and we're not talking about porn, we're talking about out-of-order packets, runt packets, bad checksums, just really dirty networks that actually exist in production environments in large organizations out there. So the real world still surprises me to this day. And there's other approaches to IPS. So there's, with 2.9, and we'll talk a little bit about it, the folks at SourceFire have taken a really, I think, promising approach to TCP and IP normalization. So if you can assume that you're an inline device and you're actually rewriting the packets as they traverse your device, you're all of a sudden free to essentially eliminate any of the ambiguity there. So it's in the TCP protocol, you can cause ambiguous reassembly conditions. For instance, you could have two different segments that overlap, essentially duplicated segments that have some bytes of the window that are overlapping. Different strategies or different stacks will choose to reassemble that different ways. The challenge of an end device is essentially you've got to model every single peer and the strategies, their stack, and the bugs in their stack, the peculiarities of their stack, and how they're going to resolve ambiguous conditions like these. So on to Snort. It's the world's most popular IDS IPS. It's quite mature. I mean, I want to say the early releases were in the late 90s that Marty was pushing out there, and now they've built a large publicly traded corporation with the recent NSS Labs reports. Very impressive performance there. And the architecture is a streaming architecture, contrasted to some other approaches around building state machines to process the packets byte by byte. I think one of the reasons Snort really took off is that it offered a relatively simple rules language that was human readable, that people could just sit down and start writing rules. And it sort of lowered the playing field. At that time, a lot of these solutions were highly complicated, had obscure formats, almost you were programming to develop network countermeasures. When Marty released Snort, he basically decided to create a pretty straightforward rules language that you could read and write yourself. And I think that really led to a lot of the popularity. It's got a whole framework of different decoders and normalizers. Today, probably the biggest one that people talk about is the HTTP normalizer, back to the web threat and the threat at the application layer. High performance set-wise pattern matching algorithms. I think there's different flavors now for low memory conditions and different mixtures of performance and memory. And you can dynamically extend the capabilities of the engine quite easily at runtime through shared objects such as dynamic preprocessors or even Snort dynamic rules. One advantage of the dynamic rules is it's a way to obfuscate what the network countermeasure actually is. So there are certain scenarios where I can't say it's going to hide the details of the countermeasure, but it's definitely going to raise the bar, and someone who has that shared object is going to have to go to some trouble to figure out exactly what it's looking for there. So sort of a high-level model of the Snort architecture there. In reality, I think the SSL preprocessor is really not at a separate layer architecturally, and it exists mostly as performance optimization to detect when a stream becomes encrypted and then to mark it as not needing to be reassembled anymore. But if you'll notice, all the application layer decoding and preprocessing really rides on top of the Stream 5 layer. If you read the documentation for the HTTP inspect module, it basically states that it's stateless, but it does assume that there's a component underlying it that's going to handle reassembly. The HTTP module itself doesn't worry about TCP stream reassembly. It's simply presented reassembled buffers that then it's going to apply its application layer logic to. So the Stream 5 preprocessor, I'm not certain if it was a total rewrite, but it was a drastic enhancement to the older Stream 4 module. And basically, it added a whole lot of capabilities. The Stream API was extended. They recently added the normalization features to that and optional three-way handshake. Just some basic configuration options. There's extensive configuration you can put around the stream reassembly. The technique used is known as target-based reassembly. Really what that means is, I touched on it earlier, is that you're providing the engine information about the endpoints so that it can model their behavior. Typically, that's done at scale using what's known as the host attributes table. There's some tools out there to build that, the commercial RNA product, but also there's some scripts to build it from Nmap and Nessus output. And the hope is that some of that really hot RNA technology will be open source in the future to make it really easy to build these tables. But basically, you're telling it this IP address is a web server. It's running web services on these ports. It's an IIS server. And here's how I want you to configure the decoding of that. So just back to basics. Why do we need to reassemble TCP streams? Well, basically, when you're writing network countermeasures, you're looking for some payload on the network. It may be separated across many packets. Those packets, those TCP segments will be separated against multiple TCP segments. Those segments might be fragmented into multiple packets. So really, you can't let the rule writer have to worry about all these details. The snort model is that there's an underlying preprocessor that's going to make its best effort at putting this together before the rule engine applies that packet. Out of order packets, retransmissions, overlaps. It's a nasty network world that you have to worry about. So one of the things I learned, and Ashley taught me about, was different flush policies, basically. And so there's four flush policies defined in the source code of the stream module. The flush policy, as far as I can tell, it's determined at compile time. However, you can modify it at runtime using the stream API. Typically, that would be from within a preprocessor. So the default flush policy. First, what is stream flushing? Well, basically, you have packets, actual packets as they are on the wire, arriving at the engine. The stream reassembly algorithm or the strategy has to determine when it wants to decide to attempt to reassemble the queued packets, and also when to flush that reassembled buffer. So two strategies. When do I want to do the reassembly operation, and when is it okay to flush those reassembled packets and then basically clear that buffer? The default policy is around footprints. So what a footprint is, it's essentially the difference between the base sequence number and the last acknowledged sequence number. It's the set of bytes that have been acknowledged from the other peer. That's essentially the stream footprint for an ongoing TCP stream. The way Snort does this is it reassembles a stream bidirectionally. If you can think of it, there's a stream going from the client to the server. That is the TCP initiator and the TCP listener. And there's going to be a stream headed back from the server to the client. They're really considered separate streams that are reassembled with possibly separate different flush point values. So all four of these strategies focus on acknowledgements. Basically, the reassembly operation is triggered by the acknowledgement from the remote peer. And then the reassembled buffer is flushed per the flush strategy or the flush policy. This first one, the default, when an acknowledgement is received for a TCP segment, the engine goes and checks to say, okay, is it time for me to do a reassembly operation? There's a little bit of logic there we'll talk about. And then basically, if the footprint is larger than that flush, if the footprint is greater than the flush point, then the reassembly will occur. Otherwise, it may wait for a further acknowledgement to be received before it decides that actually it's worthwhile to do this expensive operation of reassembling these packets. And the key there is it's reassembling acknowledged segments. Segments that the remote peer has sent a TCP ACK packet for and said, yes, I received that loud and clear. The other strategies are a little bit different. The logical, the stream FL policy logical is very similar to the footprint policy, except instead of using the footprint, the queue of acknowledged bytes, it uses simply the queued bytes. There's a variable called seek underscore bytes underscore logical. And I believe, I see SourceFire people out there that throw stuff at me, keep me honest. But the logical strategy is basically, instead of the footprint of acknowledged bytes, it's basically just looking at the queued bytes on that stream. The sliding window policy is different in that the buffering logic, the flushing logic is different. It's not going to flush the entire buffer when it reassembles. It basically flushes part of the buffer and moves the window down. in that sliding window strategy. And the response policy, I don't have a whole lot of information about, but it doesn't seem to be used anywhere in the code base today. But it's important to note that all 4 of these are based on acknowledgements. So it's, as you can think through the implications of this, it's very, very important to know when to flush. I was doing a little bit of Google image search for this talk, and lo and behold, Joe Grand of the Grand Idea Studio had built a robo-flush toilet at some point. So, this seemed just appropriate to be talking about flushing buffers here. 2 challenges in terms of stream reassembly around acknowledgements. So you could think that waiting for an acknowledgement to really inspect data makes a whole lot of sense for an IDS, in that if you don't do that, the attacker could inject garbage packets that will never be acknowledged by the endpoint, that will be discarded by the endpoint. So 1, why should you bother inspecting those and sucking up performance? 2, those packets could potentially be crafted to cause you to alert and cause false positives where the actual attack was not distinguished. But acknowledgement-based reassembly doesn't always work so well for IPS, in that an attack may be fragmented across multiple packets, but you may have actually let some of that attack, or in certain strange corner cases, all of the attack, go through the inline device before the key pieces of that attack are acknowledged, reassembled, and then the attack is actually detected. And then it gets more complicated when you look at the different flush strategies and how those interact. So Snort introduced the TCP normalizations, I think, in the 2.9 release of Snort. And it looks like it only currently supports the default footprint strategy. The difference there is when you're running the TCP normalization mode, you're reassembling on the receipt of data segments. So really, it's the strategy of the reassembly has been modified to kind of fit an inline operation a little bit better. So instead of waiting for these acknowledgements coming back, literally when the normalizing, when the stream reassembly engine with normalization mode receives these frames or data segments, it's going to go ahead and try to reassemble and see if there's an attack in there, not wait for the attack. And so back to the flush points. You can imagine if, as an attacker, I could cause the buffer to be flushed before a final part of my attack is acknowledged, then I might be able to get my attack across the detection engine. So the question is, when is it appropriate to flush the buffer? And this goes back to design trade-offs. The bigger this buffer gets, the more performance intensive the inspection is going to be. The bigger you let the buffer get, the more packets could be queued up. So again, the more intensive the reassembly operation is going to be. And also you can have some complex situations of overlapping or TCP ambiguity that can be expensive to resolve. So I found a post, and I only found this post when it was referenced from a later post, but back in March, a gentleman by the name of Yan Zheng Hu posted a query to the, I think that's the Snort developers list, not Snort users, and he had a very well-written test case where he had a Python script that was sending small packets, acting as a web server, delivering a malicious PDF. And he found in certain scenarios with those small packets, his rule that he had written just wasn't working as he intended. So he laid out his test scenario there, and I wasn't able to find a response on list to this gentleman. There could have well been a response off list. And then he referenced some source code in his post. One source code is, how are these flush points determined? Well, it's a pseudo-random selection of a static array of flush points, as you can see there. Obviously, if you're going to recompile Snort, you can modify these values. You can change the strategy. And then he also found that, as I spoke about before, the default policy is not going to reassemble until the footprint is greater than that flush point. So in late October, a gentleman who posted the Snort developers list by the name of Lord Schodelmort started a thread talking about HP inspect and packet reassembly. And he had a particular test scenario where he had a malicious response from a web server, and the last key part of that malicious response was, well down into the response, well past a flush point. Both of these posts were hinting at symptoms of a problem, and they were speculating about what the problem was, but they were basically looking at shadows of what the actual issue was. So if Lord Voldemort is here at Shmoocon, I will buy you a drink at the hotel bar, but you just have to approach me sometime and have a conversation. So basically, this started a thread on the Snort developers list, and I think Matt from SourceFire came on board and said, hey, we're aware of this issue, and it will be fixed in a future release. It appears the issue was fixed in Snort 2.9.03 or 02. Ashley Thomas reported this in parallel privately to the Snort developers, and there's a particular bug I'll show you that was fixed a few months ago. So here's a code snippet. I think this code snippet is from Snort 2.8.4.1. I'm not sure exactly when it was introduced. But the key there is that if statement. This function itself, flush act, is basically the function that gets called when the reassembly operation is triggered. And it basically makes a determination in this if statement of whether it makes sense to attempt a reassembly operation. And so, just on the surface, you can imagine, well, if I only have one packet queued, it probably doesn't make sense to reassemble. Why would you reassemble if you have one packet queued? But this code didn't really anticipate the case where packets and their acknowledgements don't happen sequentially. So if you can imagine in sequence 1 on the left, where you send a packet to the server, and before the acknowledgement to packet 1 comes back, you send another packet. So you transmit packet 1 and 2, acknowledgement to packet 1, and acknowledgement to packet 2 come back. So if you go back to this code, imagine packet 1's been sent, packet 2's been sent, there's 2 packets queued in the reassembly engine, and the acknowledgement to packet 1 comes back. The reassembly engine sees the acknowledgement and says, acknowledgement, this is when I need to consider reassembly. It checks, does the segment count equal 1? No, it equals 2. I've got 2 packets queued. It goes ahead and reassembles. Using the default footprint strategy, you only reassembled acknowledged segments. So while you have 2 packets queued, only 1 is acknowledged. You run the reassembly operation on 1 packet, flush the buffer, and then you receive an acknowledgement for packet 2. So the content between packet 1 and packet 2 will never be inspected together. And this all happens because 2 combinations, the acknowledgements and the packets weren't sequential in that the acknowledgements arrived out of order with the packets you transmitted, but also this slight logical flaw. The correct check, I believe, would have been if the count of acknowledged frames equals 1, don't bother. So it looks, this section, Ashley told me was pretty much rewritten. There wasn't just a little point change. This logic was refactored in 2903 or 2902. And this case has been eliminated. But you can see, I'm trying to imagine as the developer wrote this, it seems like a very reasonable check, a sanity check. But if you don't consider the actual strategy you're using around acknowledged frames, then you can get in this mismatch scenario. So Ashley was going to attempt a live demo here over a VPN connection back to some VMs in Atlanta, Georgia. I've chosen that would be unwise for me to attempt that here. So I'm going to walk you through a scenario that will illustrate this kind of this issue. So imagine, if you would, this is some vulnerability from 2005. I don't have the CVE number on the top of my head. Just a buffer overflow and an IMAP service. You're going to send the authenticate command. You're going to send a whole bunch of A's, old school, and then finally there's going to be some hexadecimal code that's part of I think that was part of the shell code that was delivered back in 2005. So we're basically going to look at this scenario of sequence 1. With this attack, to basically cause this scenario to play out, You could try to use something like frag route. What you can do simply here is just like on the server, set the MTU to 1,500 bytes, for instance. And in this case, where we're sending a 1,500 and something odd byte payload, that's going to actually cause the server to fragment that attack across 2 different frames. And also, with that MTU setting, we saw pretty reliably, we'd get these acknowledgments, not always, but we'd get these acknowledgments in that sequence you see on sequence 1. So, yeah, okay, connect, 3-way handshake. I apologize for the lack of detail on these slides, but packet 1, which contains the authenticate and the capital A, the 041 overflow. Packet 2, the first packet is 1,368 bytes. If I had a laser pointer, I'd show you. And then the second packet has 178 bytes of TCP data. So basically, that shell code is in the second packet, and the authenticate command and all those A's are in the first packet. So we see packet 1 transmitted, packet 2 transmitted. We get back the acknowledgement to packet 1. We get back the acknowledgement to packet 2. Server crashes, do the overflow. We see a reset come back from the stack after that server crashed. So what just happened? We had this snort rule that was intended to catch this, 1,500 odd byte attack. But when the acknowledgements with the server had a 1,500 MTU and the acknowledgements come back in this order, we failed to detect the attack. We failed to block it. When we look at the actual packet payloads, the sequence numbers 1 to 1369 has those authenticate packets. The second one from 1369 to 1547 has the shell code. You can also cause a similar situation and split it across multiple packets. For instance, if you set the MTU to like 576 or so and ran the same sample, you would be split into 3 packets. And again, we'd see this issue where the acknowledgements trigger in the older snort code from 1 or 2 point releases ago, that mismatch between the check, the sanity check for 1, and basically the strategy that's being used by default. So like I said, there's 4 strategies that are embedded into snort. You can write a preprocessor, and then on the flows of your choosing, modify the flush policy that's being used. Or you can simply go in and start playing with these policies and recompile the engine itself. Without the demo, that pretty much delivers the content I had prepared for you. We have about 10 minutes for question and answers here, and I would be looking for some questions to help illustrate this corner case. No questions from my DC 404 people? Nothing? Silence? Ducky, you look curious. Yeah. So I haven't really even played with the 3.0 beta, so I'm not certain. I've seen the early ones. It says that basically the Snort 2.x detection engine is a plug-in to the core of Snort 3. So who knows? So there's some areas for further research around the acknowledgements, and I would encourage people to look closer at how the normalization preprocessor is working. And it seems very promising. If you can assume an inline IPS position, then why not? Why not just deal with all the ambiguous TCP scenarios and not have to worry about reassembling necessarily based on the targets, but based on what your strategy is. So I think with further development, the normalization strategy is going to be excellent for inline devices, but it's not a full solution because the majority of Snort installations, open source Snort installations, I believe, are in IDS mode. So really you need 2 strategies that are going to work in either detection or prevention. So that's configurable today in the latest Snort release. You can do -- enable normalize and configure IPv6, IP, and TCP and ICMP normalizations within the stream engine. And so basically overlapping segments in some of these scenarios are going to be dealt with by the engine. It's not perfect, but it's a large step forward than trying to passively reassemble the ambiguity of the TCP streams. All right, well, I hope to meet Lord Choldemort this evening. Thank you.